Let's get started with lecture 24. So last time we started talking about interference in 2 and 3 dimensions. So the idea was that basically the phase of the individual propagating waves, the phases of these individual waves depend on the distance from the source and the phase constant of the source. So if you have a source, you have waves kind of propagating in a symmetric way, so they form these circular or spherical in 3 dimensions wavefronts. And all wavefronts have the same phase. So you have like the same number, let's say that's a wavefront corresponding to a crest. All the points on it have the same phase, so you have the same number of wavelength from the source. So we wrote phase for one point to be equal to 2 pi r over lambda, where r is the length of the vector connecting the source to that point, and well, plus a phase constant phi naught of the source. Therefore, the set of all points that have the same phase will be a circle in 2 dimensions, because that's the set of all points that have the same r, and then a sphere in 3 dimensions. So then, if we have multiple sources, we talked about adding these waves, finding the superposition of the waves propagating from the 2 sources, for example, and we found that if sources are in phase, then the phase difference at one point between the waves arriving at that point from the 2 sources is just given by 2 pi lambda times the difference between distance traveled. So, for example, if you have one source and you have one wavefront here, let's say of radius 2 lambda, you have another wavefront, let's say that's the other source here, of radius 3 lambda. This point that's on the 2 wavefronts is a distance 3 lambda from this source, a distance 2 lambda from the other source. So the difference between distances is just lambda, and that gives a phase difference of 2 pi. And those 2 sources clearly interfere in a constructive way. First, we can just visually see that we have 2 crests. These are 2 wavefronts. And also we can check the phase difference, and it's a multiple of 2 pi. So that's constructive interference. So maximum constructive interference had a phase difference that's an integer multiple of 2 pi, and destructive is the case where they're out of phase, so that gives again an integer multiple of 2 pi, which doesn't do anything, plus pi, right? So when you shift the sine wave by pi, say from here to here, the phase changes by pi. So if I shift it by pi, then here I get this pattern, and they will be out of phase and completely cancel out. So that's destructive interference. And we played with a couple of examples trying to find the positions in space where we have destructive interference and when we have constructive interference. And we called the set of all points with destructive interference, we called it a nodal line. And points with maximally constructive interference, say maximally were the antinodal lines. So basically, for nodal lines, we get zero amplitude. These are dark spots if we're talking about light, or places, or quiet places if you're thinking about sound. Or if you're thinking about water ripples on a lake, it's the points where water kind of doesn't fluctuate, it's just flat, stays at the equilibrium position. And the antinodal lines are the places where you have the largest possible amplitude for the oscillations at that point. So you would see like the brightest parts if you put a screen and you're talking about light, or if you have a sound detector, you have the highest intensity, you would hear a louder sound, etc. All right, so we had a little bit of practice kind of finding these nodal lines and these antinodal lines. And for two sources with fixed phase constants, really what determines whether you are on a, let's say, nodal line, for example, is the difference between distances to the two sources, right? So if you have source 1 here and source 2 here, and if you think about one given point that's a distance r1 from one source and distance r2 from the other, well, r1 minus r2 determines the phase difference between the waves arriving at that point. So if this point is, let's say, on a nodal line, if there's destructive interference, which means the phase difference is pi, up to some factor of 2 pi, then all the other points in space that have the same r1 minus r2 belong to the nodal lines. This nodal line this point belongs to, right? So if you have one point where there is destructive interference and it has a given r1 minus r2, if you find all other points in space that have the same r1 minus r2, they belong to a nodal line, and where this point is on that nodal line. So each nodal line can be labeled by r1 minus r2, right? So you may know from geometry that a curve like that in general is known as a hyperbola. So there are these conic sections. So if you have a cone, so let's say you have a cone and the cross section of a plane with a cone forms various conic sections. So if you have a plane like that parallel to the base, then it gives you a circle. If it's at some slight angle here, it's an ellipse, which is a set of points where the sum of distances from 2 points is the same. And then if it's parallel to this, to one of the sides, one can show it's a parabolic curve. And if it's even like more sloped like that, you form a hyperbolic curve. So we're not getting much into the geometry of that, but it's good to know what these curves are. All right, so let's practice a little bit, and that's something that you also practice somewhat in the lab with this setup. So let's say I have two sources and they're now right on top of each other. So I just see one set of wavefronts. So let's say the solid lines are the wavefronts, the dashed lines are the troughs between these crests. Okay, so right now everything is in phase, right? At every point I look, basically all wavefronts are right on top of each other. So at every point in space, the phase difference is 0 because R is the same, the sources are the same. Now, suppose I take one of these sources and move it. So this is just a graphics program called Inkscape. And you see the distance between wavefronts is lambda. And in the units I've drawn this, lambda is 50. I guess that's in pixels or whatever it is. Yeah. All right, so if I take this and move it maybe by 1/5 of lambda, by 10 pixels, see that not much happens, right? They're not right on top of each other, but pretty much like all the points, you know, where you have a positive amplitude from one, you also have a positive amplitude from the other. When you have a negative amplitude from one source, you have a negative amplitude from the other. There are some areas like here when, let's say, these wavefronts overlap where you have maximally constructive interference. So this vertical line, and that makes sense, it's the same distance from the two sources. But we don't get destructive, right? To get destructive, we need like a maximum to overlap with a minimum. So we need to have a crest overlapping with a trough. So let me increase that to 20, which is less than half of the wavelength. And we still see like none of the solid lines from one source is overlapping with solid lines from another source. They're getting very close. Sorry, they're overlapping with dashed lines from the other source. They're getting very close, as you can see, but they're not overlapping. So if I make this point, make it 25, which is half of the wavelength, now I see that these dashed lines can cross the solid lines here. So it seems this horizontal line here and here will be a nodal line, will give me destructive interference. Then let's increase that to 50, which is 1 lambda. So yeah, what is the fate of those lines? They go here, right? They kind of open up like that. And see, these are the points where a solid and a dashed cross. And kind of they look lighter just visually if one stares at them. And if you increase that quite a bit, so let me go to, for example, 150. Now we have quite a few more of these sets of nodal lines that arise. So you will get quite a bit of practice with this in the lab with the same setup. So let's think a little bit more. So for example, consider sources that are in phase, right? And let's say the sources are at some distance L from each other. So the first nodal line that we would get is when delta R is lambda over 2, right? The second would be delta r is lambda plus lambda over 2. This gives a phase difference of pi. The next one gives a phase difference of 3 pi, which is pi plus 2 pi. Etc. So we may ask ourselves, how does that distance relate to the nodal lines we get? Can we have any difference in the distance? And the answer is no. So for example, if L is 0, right, delta R is always 0. The only allowed value of delta R is 0, so you can't get any of those. And it makes sense that as you increase L, the distance between the sources, more of these possible values of delta R, which can lead to destructive interference and give us nodal lines, become allowed. So how do we make sense of it? Well, you know, if you have these sources, a distance R, a distance L, and there is R1, R2, and L here, right, there's a basic result from geometry known as the Triangular Inequality, which says the sum of two sides of a triangle can never be smaller than the length of the third side. So that means, for example, that R1 or R2, let's say, plus D is plus L, rather. Again, in the lab, you will think a little bit about the derivation of this and where this is coming from. R2 plus L is larger than or equal to R1. I'll clean up my 2 here a little bit. R2. So that means if you take R2 to the other side, it means R1 minus R2 must be smaller than or equal to L. So that's delta R is smaller than or equal to L. So basically, we can this way predict, how many nodal lines you get, right? So the allowed values of delta R, which give us a nodal line, are these odd integer multiples of lambda 2. So we can have, let's say here we have 0, here we have L, right? So let's say here you have lambda over 2, here you have 3 lambda over 2, and then if 5 lambda over 2 gets larger than L, then we can't have a nodal line with delta R of 5 lambda over 2. So basically we need to find the largest odd integer m such that m times lambda over 2 doesn't go over L. So yeah. All right. So let's go back to our slide. So the model of interference, again, for two waves, right? This is a useful model to visualize. We draw pictures of the sources and the points where the waves interfere. And we find R1 and R2, the distance from the source to that point. If there is some phase difference, some difference between the phase constants of the two sources, we take that into account, and then for every point we should be able to find the phase difference between the waves arriving at that point, right? And knowing that phase difference allows us to decide whether the interference is destructive or maximally constructive. So that's the condition. If that phase difference is a multiple of 2 pi, then it's maximally constructive, and if it's a multiple of 2 pi plus a pi, then it's destructive. They're completely out of phase and add up to 0. Okay, so here's a problem. So let's read it together, and then I'll ask you to pause the video and work through this problem. So we have two loudspeakers in a plane that are 2 meters apart and in phase. So in phase means the difference between their phase constants is 0. In phase with each other. So both emit 700 hertz sound waves into a room where the speed of sound is 341 meters per second. Okay, so we know the frequency, we know the speed. Then there's a listener 5 meters in front of the loudspeakers and 2 meters to one side of the center. All right, so we know where the listener is. So the question is, what kind of interference do we have where the listener is? And how would things change if the loudspeakers were out of phase? So pause the video, try to work this out, and we'll come back and go through the solution together. All right, so here's the geometry. Here's the figure we would draw from that description, right? We have two loudspeakers, 700 hertz frequency. They're 2 meters away from each other. And the position of the listener is 5 meters in front of them. So if you take the point halfway between the loudspeakers and move 5 meters this way, or that's going to be a line 5 meters away from the line of the loudspeakers. And we also know that it's 2 meters away from the central line. So we know where the loudspeaker is. We know the frequencies, we know the speed, and we know that the phase constant difference is 0. Okay, so let's go back to the notes. That's example 1710. So that's source 1, that's source 2, this is 5 meters, 1 meter, 1 meter, this is 2 meters here, and that's where the listener is. Okay. So we want to find the phase difference, right, between the waves arriving at that point. So first we have to find the distances from the sources to that point. So if you have a distance r1 from this source to that point and a distance r2 from the other source to that point, we need to solve a geometry problem and figure out what these distances are. Okay, so how can we figure it out? Well, we're given a bunch of vertical and horizontal distances, right? So it seems it should be easy to make that distance the hypotenuse of some right triangle where we know the other sides, and then use the Pythagorean theorem to find that length. Okay, so for example, if I look at this right triangle, if I draw a line here horizontally, well, I know from here to here I have 1 meter, from here to here I have 2 meters, so this distance from here to here should be 1 meter. And then I have my triangle, so this side is 5, this side is 1, so R1 should be square root of 5 squared plus 1 squared, that's square root of 26 meters. Similarly, R2, well, again, I play the same game. Now I have 2 from here to here plus 1, so that's going to be 3. And the horizontal distance is 5, so that's going to be the square root of 5 squared plus 3 squared. Not 3 to the 9, 3 squared, which is 9. 3 squared. So 25 plus 9 is 34. Okay, so we have those. And we know delta phi is delta phi naught, which we know is 0 because, at least in the first part of the problem, we're assuming the sources are in phase, plus 2 pi over lambda, and then we subtract the larger one from the smaller one just to write a positive thing. So that's going to be square root 34 minus square root 26. And this is going to be in radians if we put lambda in meters, right? Okay, so how do we figure out what the wavelength is? We don't know what the wavelength is, but we know the speed, and we know the frequency, and we know that lambda is v over the frequency. So that becomes 341 over 700. So that's going to be some number in meters, right? Because 341 was meters per second, 700 is hertz, which is 1 over second. So the second goes away and we're left with meters. Okay, so if we just find that number and see what it is, then we can compare it with the criteria for constructive and destructive interference or something in between. So let's go back to the solution and see what those numbers are. All right, so yeah, so that's one is 5.83, 5.10. This is that. Okay, so we just plug in the numbers. And it turns out delta R is 3/2 lambda. So delta R is 0.73 meters. Lambda is that, so 1.5 times this. 1.5 times lambda is that delta R. So therefore the phase difference becomes basically pi, right? So that's, or becomes 3 pi, which is equivalent to pi. Remember, factors of 2 pi don't matter, right, in a phase. So that's the condition for destructive interference. And now, if the sources were out of phase, you're putting in another pi, so add that pi to your 3 pi, you get 4 pi, which is a multiple of 2 pi, and that gives rise to maximally constructive interference. So the phase constant is quite important, right? The phase constant of pi always switches between constructive and destructive. Can turn a nodal line into an antinodal line. All right, so the last topic I want to talk about today is a phenomenon called beats, and it's quite a simple interference phenomenon. So it's basically if you have two waves, two sources, which have a different frequency but very close frequency. Okay. And then you put them close to each other, and then we look at the interference pattern, or if there are like loudspeakers or sound source, which is a classic example. So you can do this with two loudspeakers. Basically, one would hear kind of modulation. The sound keeps getting louder and lower. Goes up and down, like the intensity goes up and down. And that's with a kind of a smaller frequency, much smaller frequency than the actual frequency of the sources. So it's loud and soft. And And this directly follows from, again, just writing a sum of two sines as a product, right? So we can always do that. So we're going to get one of the terms in the product. So we're going to get a product of two sinusoidal functions. One is like a cosine, the other is like a sine. And one has a high frequency, the other has a small frequency. So once you multiply this small frequency one, gives you like an envelope like that. And then you have, in each of these oscillations, you have a lot of oscillations from the other one. But the low frequency oscillations give rise to this beat phenomenon. Okay. So the frequency of the beats is just a difference between the frequency of the sources. So to understand the phenomenon of beats, let's just consider two sine waves with the same amplitude. So let's say D1 is a sine k1x minus omega 1t plus some phase constant, and D2 is a sine k2x minus omega 2t plus phi 2 naught. Okay? And as we said, because they're propagating in the same medium, these are not entirely independent, so we must have omega 1 over k1 to be equal to omega 2 over k2 to be equal to the speed of propagation. So these are two sine waves going from left to right, and they're general, except we assume we have the same amplitude for simplicity. All right, so then D, the superposition, which is D1 plus D2, is going to be, let's call this whole thing phi 1, this whole thing phi 2, is going to be a sine phi 1 plus sine phi 2. So if we remember the trig identity we used before, it's going to be 2a sine of the sum of the phases divided by 2 times cosine of their difference. So this is 2a. We're going to have sine, let's say, k1 plus k2 over 2 times x minus omega 1 plus omega 2 over 2 times t plus phi 1 naught plus phi 2 naught over 2. And this multiplies cosine k1 minus k2 over 2 times x minus omega 1 minus omega 2 over 2 times t plus phi 1 naught minus phi 2 naught over 2. I'm going to make it a bit smaller so you can see the whole equation here. All right, so that's the superposition. So it's a product of two waves, both of which are propagating at the same speed v, which makes sense, right? So you have two waves, each propagates at the same speed v, and it forms a pattern, so that whole pattern must be shifting forward at some speed v. And that's because, you know, if the ratio of omega 1 to k1 is equal to omega 2 k2, then we can write omega 1 plus omega 2 over k1 plus k2 is equal to omega 1 minus omega 2, where k1 minus k2, that's also the same speed. Now, if we look at the, let's say the history graph, so we fix x, Right, with some phase shift, we're gonna show, let's say, his history graph here. So we get a sine function like this. So we have, so let's say this is just a sine term. And the whole difference between, if you fix x, this whole thing is some phase shift, right? k1 plus k2 over 2 times x plus phi1 plus phi2 over 2. And this has a different phase shift. So we're going to get a sine and a cosine, and they have different frequencies, right? So the frequency of this one for the sine, the frequency is going to be this thing here. That's the angular frequency. Frequency is just the angular frequency divided by 2 pi. So it's going to be omega 1 plus omega 2 over 2 times 1 over 2 pi, which is also f1 plus f2 over 2, right? The average frequency of the two waves. So let's say this is time, this is the history graph, this is just that sine function, and that's a high frequency, right? It's much higher than the frequency of the cosine term. So the cosine term, it has some arbitrary phase shift. I don't know, it's probably maybe, let's say here, it's going down that way. But it has a much, so that's the cosine term here, this cosine. And that has a small frequency, right? The frequency is the difference between the frequencies over 2. So it's going to be a much more spread out. It has a longer period when it has a smaller frequency. So that's the cosine term. Again, that's the history graph at some point. And they're shifted. There's some arbitrary phase shift because we're at some position. So yeah, they give different numbers and presumably there are different phase constants. But here, f, so let's call this f sine, and this is f cosine. This is f1 minus f2 over 2. So now you multiply this, and you multiply the whole thing by 2a. So now if you think about dA, it's going to go between 2a and minus 2a, so that's, let's say we multiply the cosine by 2a, that gives us this envelope that goes between minus 2a and 2a, and then it multiplies the sine, so we're going to get these kind of fast oscillations within that envelope, and the sign can go between plus and minus 1, so it's going to look something like this, right? These are the faster oscillations from the higher frequency sine factor. So by just writing the sum of two sines as the product of a sine and a cosine, we can figure out the pattern of the history graph, and the snapshot figures would look the same. Would look similar, except instead of frequencies we have wave numbers k for wave. Yeah, same pattern happens for history graphs, except instead of omega 1 plus omega 2, now the relevant coefficient is k1 plus k2 over 2. Okay, so now if you're thinking about sound and you put a sound detector at some point and you think about what you're going to hear, what you're going to detect, what matters is the history graph we talked about. And so this thing, f cosine, is also known as the modulation frequency. F modulation is f1 minus f2 over 2. Now, we're going to hear beats. We're going to hear a loud sound over here and over here, right? So for one full period of this cosine term, of the low frequency factor, we're going to hear 2 beats. So the frequency of the beats we hear must be twice that, right? It's 2 times F modulation. It's period. The period corresponding to the beats is half the period, right? So this is, let's say, from here to here. That's the period corresponding to modulations. And then for each full period, we're going to hear 2 beats, right? This sine is going fast between -1 and 1. So both a minimum and a maximum, they give us the highest intensity. So that's T beat, which is half. So then the period, then the frequency is 1 over the period, so it becomes twice. And finally, we end up with this F beat being F1 minus F2. So here, I assumed this was, we had a hidden assumption. Hidden assumption was F1 is larger than F2. So the most general case is, you know, call the one that's bigger F1. So then we're going to get a positive number for this beat frequency, which is the absolute value of F1 minus F2. So if F2 is the larger one, we're going to get F2 minus F1, right? So thinking about the absolute value, this is F1 minus F2 for F1 larger than F2. And it's F2 minus F1 if F2 is larger than F1. All right. So that's the theory of the beat sender, and we come up with this simple formula for the beat frequency. All right. So here's a quick question. So yeah, read through this, pause the video, and then we come back and discuss it together. All right, so you hear 2 beats per second when 2 sound sources, both at rest, play simultaneously. Okay. The beats disappear if source 2 moves toward you while source 1 remains at rest. Okay. The frequency of source 1 is 500 Hertz. What is the frequency of source 2? Okay, so that's an interesting question, right? So when they're both next to each other, they play simultaneously, we hear 2 beats per second. So the beat frequency is 2 Hertz. And then we know source 1 has a frequency of 500 Hertz. So source 2 is either 502 or 498. It has sort of a frequency that differs from the frequency of source 1 by 2 Hertz, which is the beat frequency that we hear. Now the question is, does it have a higher frequency or does it have a smaller frequency? So there's some more information, right? It says if source 2 moves toward you, the beats disappear. So if source 2 moves toward you, its frequency becomes the same. For you, the frequency you perceive becomes the same as the 500 Hertz frequency of source 1, and then the beats disappear. Okay? So moving toward you, what does it do? If you remember the Doppler effect, when a source moves toward you, the wavelength shrinks, it has to be compressed, so the frequency goes up, right? So when it's moving toward you, you would hear a higher frequency, and that higher frequency becomes the same as 500 Hertz, and then the beats go away. So it must have, when it's stationary, well, I mean, the source must have a smaller frequency. The frequency we perceive is not the frequency of the source. So it must have a smaller frequency so that when it moves toward you, what you hear is a higher frequency. And therefore, of the two possible answers, which we could have figured by just this information that the beats have a frequency of 2 Hz and one source has a frequency of 500 Hz, of those two, B and D, this extra information related to the Doppler effect allows us to find the correct answer, which is B. Okay, so we can wrap up chapter 17, and then we'll move on to physical optics or wave optics in the next chapter. So let's briefly look at these summary slides for chapter 17, what we discussed in this chapter. So we talked about, first we started the chapter talking about the principle of superposition, which simply says that the displacements add up for waves from different sources that propagate in the same medium. We talked about standing wave, a particular pattern of superposition when you have two counter-propagating waves with the same amplitude, same frequency, same wavelength. And yeah, they give rise to this pattern that doesn't really propagate. It just moves up and down. We have nodes, we have antinodes. We found that the distance between nodes is half of the wavelength of the individual components, the individual counter-propagating waves. We found that the amplitude has this position-dependent expression. We played quite a bit with boundary conditions. So if you had fixed boundary conditions where the displacement is 0 at two boundaries, then the wavelength can only be certain quantized values, right? So you can just fit an integer number of lambda over 2's inside your length. So your length must be an integer times lambda over 2. And then that can allow for certain frequencies if the speed is the same, for a given speed rather. So this is related also to musical instruments. We talked the fundamental frequency, the lowest possible frequency is quite important. It's often the dominant sound that we hear. We also talked about other boundary conditions, kind of free boundary conditions, which had the derivative of the displacement going to 0. So then you get an antinode at one of the ends. And we had different conditions for allowed frequencies in those cases. So you basically have, like, you must fit a lambda over 4 and an integer number of lambda over 2's. If you have, let's say, fixed and free. All right. We talked about more general interference problems in higher dimensions, in 2 and 3 dimensions. So it gets a bit more complicated. So the distance from the radius is really what determines the phase of each propagating wave from a given source. And we figured out the conditions for destructive and constructive interference. So there are some phase shifts that depend on the difference in the path traveled from the two sources, so the point where we want to find the interference pattern. So if the phase shift is a multiple of 2 pi, it's constructive. If it's n plus a half times 2 pi, which is 2 pi plus a pi, then it's destructive. So those are the allowed wavelength and frequencies for various boundary conditions, either closed-closed or open-open, or open-closed and closed-open when they're different, and we're going to get different conditions. So in one case, the frequencies are just all integer multiples of f1, so they're m times v over 2l. In this case, it's an odd integer multiple of v over 4l. So fundamental frequency is v over 4l. And finally, the last topic we discussed was beats. We talked about it today. So it's basically just a simple consequence of using a trig identity writing the superposition as a product of a sine and a cosine, and the lower frequency term gives us a modulation, and then that gives rise to beats with this frequency. Okay, so let's stop here, and we'll start talking about physical optics in the next lecture.